Shall we look together at some of the questions for the exercise, or shall we move on with? Okay, so we'll do that. People nodding. Okay, so there are a couple of questions that I asked. So the reference in time and space, that was one of the questions that is there. I guess you did what was above, right? So the reference in time and the reference in time is actually the first image, and you can derive that from the data set here. So you get layer information, and the reference acquisition period is from the 3rd of June until June 2022, and this is the 3rd of June. So the reference date in this case is the first image, right? The reference point, that's something different. Now what you can do here, let me see, show reference points over here. So if I switch off these things and I say show, let's see, show reference points. Yeah, so now you're going to see a grid of isolated points. And if you zoom out, at some point you don't see them that well anymore, but there is this whole grid of points. And each of these points has in common that they're actually very good, so the quality is 0.96. And we use that grid as our reference. Right, so what we want to do is to make sure that if there's an orbit error in the satellite, or if there's a trend in the tropospheric delay, then we would like to remove that. And for that we have this kind of very rough network. But even that network, that rough network needs to be sometimes tied to something else. So we don't know actually where 0 millimeter per year is. Everything is relative to each other. So, a spatial references network is determined from a selection of high-quality insert points. This is the network. And then what we do is we get a virtual reference point in this case, which is the average or weighted average of all those points. We could make different choices. We could select one particular point and say, well, we have information that this point is very, very stable, so we're going to keep that. Or if we don't do that, we can assume, okay, let's assume that over this particular area, on average, it is 0, right? So if you don't know what you can do, then you make an assumption. So related to that reference point, also my next presentation that I would like to give, and maybe I should do that now right away because it connects to this, and this particularly deals with the reference point. So, what is the problem? So, what we have are deformation estimates, which are very, very precise. We know that, but the problem is that we don't always know what we are measuring. We don't know where that point is. If we have different techniques like leveling and GPS, so usually these are different benchmarks. So often we also measure different signals. So to give you an example, if you install a permanent GPS receiver somewhere, you want to probably store it on a very stable building or on a mast which has a very stable foundation. So by definition, that GPS antenna will not see the compaction of the peat soils next to it, right? Simply because it's not connected to that. Whereas with INSAR, we will also get points from the ground. So we're measuring actually completely different signals. And also there, in the past, when INSAR started, there have been many studies where the INSAR results had to be validated. People didn't really trust it. It was new. So they said, okay, let's compare it with leveling. And there were comparisons with leveling. There are hundreds of comparisons with leveling, with GPS, any other techniques. And the problem there is that it was never a perfect match. There was always a difference. And that is partly because these different techniques measure really different things. Measurement bolts in a wall are something else than a reflection from a roof. Very often, what we also need to do is combine different techniques. So, for example, the Geodetic survey in the Netherlands is responsible for doing the laser altimetry data or the laser scanning from airplanes. They're responsible for the elevation model relative to the geoid. They're responsible for the horizontal network with GPS. Sometimes they use photogrammetry. So all these different techniques need to be combined. And if you want to do the combination, there are two possibilities. So one is that you combine it in the parameter space. So basically you're saying, okay, we have, for example, a subsidence bowl, and we can parameterize it with a couple of numbers. And with all these different techniques, we're going to measure the same parameter. We're going to estimate the same parameters. Or alternatively would be to do it in the observation space. That would mean that we're measuring really the same physical thing over and over. Now this is a problem in normal situations, because a radar reflection will never come from a GPS antenna, for example. So if we do it in the parameter space, will be difficult. So actually there is a need to look at it in the observation space. So the challenge is, can we do this combination in the observation space, meaning that we're really looking at points that stem from the same physical object? And that, if we want to do that, we need a clear, identifiable, collocated target, which has the same dynamic behavior. So if that target moves, it should be measured by the GPS and the leveling and whatever. So what we came up with is this suggestion. It's behind here. It's called an Integrated Geodetic Reference Station, or IGRS. And this is what it looks like. So basically it's a construction which has a mast with a GPS on top of it. It has a foundation to a stable layer where we can assume some degree of stability. Then it has two reflectors which are actually backflipped. That is very useful because in this orientation it will drain itself from rain and stuff that may come into it. And this top plate here is visible for laser scanning. So we have the GNSS on top, INSAR, leveling for the plate, the laser scanning, photogrammetry on the mast, tachymetry, and relative gravimetry that we do below here. And we just last week, we also installed our first station in the Netherlands where we have also absolute gravimetry. So we have then really all the techniques together. Now, we made a network of that. We have about 35 of those stations now in the country. So this is in the northern area over here. And so that means that for all these satellites with SAR sensors, we can follow that. Inside there is a little cabinet, so the radar reflections are passive. They are just simple reflectors. And here we have then the GPS receiver and a modem and power supply and so on, and some little bit of heating. Now, if you look then at the data, then this is one of those stations. In green, you see the amplitude of the signal, the SAR signal. And so that location before the station was installed, the amplitude was quite low and variable. Then when the station was installed, then all of a sudden it saw the reflector, and you have this very strong reflection. And remember the story about the signal-to-noise ratio, the signal-to-clutter ratio. That is basically what we see here in dBs. So this is now so high that we can get a precision of 0.5 millimeter for 1 sigma. On the blue, you see the line of sight displacement here on the right-hand side, where also we have random phases, so it moves all the way, all up and down. And here we get this very nice time series. So the convenient thing of this is that now we can use that particular point and connect it to all the millions of other points and make them absolute in this sense. I'll show you a picture in a minute. So here we have the combination of the GNSS data, so the GPS antenna on top of this mast is the red one, and what we get from radar interferometry, which is in blue here. And so there's quite a good correspondence. So there are two objectives with this station. The first one is that we want to keep it as stable as possible, right? So that it is really like a rigid thing, can stay there for several years. The second thing is that if it moves, we would be able to measure it, right? And that is what we apply with the GPS and the radar. So therefore, we know really how that point moves in an absolute sense. If you do the airborne laser scanning, it looks like this. So here we have points on the ground. So this is from west to east, and this is the elevation. And these little dots over here are the little dots that come from the horizontal plate. So that we tie our whole Dutch elevation network to that. Okay, so if you use that, here is an example. So this is what we would typically get from, this is a harbor area in the Netherlands where we have rates. And the initial reference point that we choose here was over here. So then we get, for example, for point 1, 2, and 3, we get elevations. Average of all these points and see how do they behave on average. So this is 34 points that I selected. And here you see the average. Now there is a bit of a seasonal signal in here. So this is winter. It's relatively stable. But then in spring, it's going down. Right, so this is, and then here in the fall it gets stable again, and then in spring and summer it goes down. So basically this is the typical effect that you see if groundwater tables go down, for example, thank you, in the summer, groundwater tables go down and the land goes down as well. What you can see if you average here is the histogram of all these rates. Now, of course, this depending on with the points you selected, you get a different histogram, but the main mode here is at 1.5 centimeters per year, but the distribution is actually quite skewed. And the final thing which is interesting if you analyze this is to look at the time series and then check through different points. So for example, now I'm looking at this yellow point down here, but if I click here to the right, I'm going to look at other locations as well. This is a single point, so very interesting because here you see that from, let's say, the fall of 2020, there is a subsidence rate, and then here it is stable again, it goes further. So you have really like a seasonal signal over here. So in the beginning I was talking about the planning activities. So for example, if you're managing this railway or if this is of concern for you, it means that if this process is going to continue, you can expect when this is going to lead to failure. The other thing which is interesting by looking at a railway is to look at the places where it crosses a bridge or a canal or so. For example, like over here, I think. No, that is not the one. Maybe here. Okay, so here you have a sort kind of bridge. Usually, if they build a bridge with a railway or a highway on top of it, then that bridge is a very big concrete structure, so it has to have a very thorough foundation. So the bridge usually is stable because it has a foundation on a lower layer, but the areas next to it not. That is the sandy ballast bed. So the green point over here is probably quite stable. Here, there's an interesting one. Whereas the red points here.
If you reduce the point quality from 0.7 to 1, we will see, especially in the middle part, something red.
Oh, okay. Okay, let me see. Point quality. Oh, okay, yeah, thanks. Here.
From 0.7.
Okay. 0.7 to 1. This one. Yeah, so you see here this greenish band, indeed. So these are all points which are relatively stable. And my expectation is that this is due to the construction of the bridge. We see that a lot also in our country. Basically every bridge has this. And also with highways, if you drive your car on the highway, you get to the bridge, then actually you have this little bump and then you go down again, right? So this is due to the fact that the structure itself subsides and the area around it not.
Try to make a displacement minus 20 millimeters here, this scale displacement.
Okay. Like this?
Yes.
Oh yeah, you see it even better. Yeah, excellent. Yeah. You see that there are other areas, right? So there are this group of points where things are moving. Yeah, so indeed in the analysis it makes a lot of difference in how you analyze it and what you're looking for. I think the point that we just clicked on was kind of interesting because it also had a phase unwrapping issue. And so this point, for example, I don't know when this railway was constructed. Is that known? Does anybody know? I heard it was quite recent, right?
No, it's about 5 maybe years, maybe.
Okay. Because from this you would deduce that, let's say, before here, let's say November 2019, yeah, before here, yeah, November 2019, it was much more noisy at this point. There was much more variability. And after that, it became stable. So probably they were making something there, or at least the point changed. That's something you can conclude. But there was also this, I forgot which point it was that I clicked on. No. Yeah, well, I'll find another one. Okay, so that is railways. Interesting thing. So also here, things are changing. This bridge is motion. There's motion. And the bridges is the other thing I would like to show you. Maybe one of the bridges here nearby. Let's make it again a little bit smaller in the range. We put the point quality back. Okay, so now we have all the points. Now what you see over here, let's take this bridge. I guess this is a familiar bridge to you guys. So what do we see? So we see greenish points over here, and we see blue over here and red over there, right? Now that suggests, so this is an ascending orbit, right? Red always means away from the satellite, so down or at least away from the satellite. Blue means towards the satellite. And we have an ascending orbit, that's the indication over here. So basically we're flying here over Poland and looking from this direction to the bridge. Okay, if this is going -5 away, so it means that it's moving basically towards that side. So either it is going down over here, and it means that the bridge is coming up over there, or it is going horizontally in that direction and then horizontally in that direction. Right? So that is, both is a little bit strange, right? Now, if you look at this, let's see what we have if we click on one of those blue points. Okay. Yeah. So this is the reason that we plot these ambiguity levels here, right? So what the algorithm did is it said, okay, from all these options that I have, I think that this straight line is the best, right? But if we're now looking at it, actually, it is much more complicated because, let me see if I can do this way. Okay, so this was the plot that we had. And actually, how you could interpret this is that, for example, if we take this line over here, then we follow it over here, then it goes up again, then it goes down again, and then it has this line. Right? This would be an alternative interpretation of this signal. Right? So the algorithm said, okay, it's going up, but because the differences between the gray and the blue lines blue dots are so small, it could very well be that there is another path through these data. So you could see this as if you use Google Maps to go to some place, and sometimes it gives you the best option, right, in blue, and then it gives you another option which is 2 minutes longer, or another option which is 3 minutes longer. That's the same thing over here. So we have basically these dots, and we can find our route through this whole time series. Most likely here, at this particular point of the bridge, the blue line is the wrong interpretation. Most likely it is this kind of pattern, and this matches with what we would expect for thermal expansion in summer and winter. Right? So basically this is a long bridge, steel construction. So in summer it's warmer, the bridge goes out, so this point goes to the left and this point goes to the right. And we can check that. Let's try that again. Huh? No, this is the bridge over here, close by. Eh? Yeah. So, but if we look at this here, so basically, what you need to remember here is that this is, let's say 2020. So this is the 1st of January. So this is winter, right? So In the winter it is low, and in the summer it's high. In the winter it's low, summer is high, right? So let's remember the winter is low, right? Now if we go to the other side of the bridge, so here the winter is low. Here. The winter was low, that was over here. Here the winter is high. See, the winter is high, summer is low, the winter is high. And again, here we have this, I cannot draw it, but I guess you can see it, right? So basically we need to start here, goes up, we go down. There's a perfect connection over here. So this solution, the blue solution, is wrong, and it follows this pattern, right? So whereas one point is coming towards the satellite, the other point is moving away from the satellite. So again, so this is what you get if you process data without knowing what you're looking for, right? So if you simply switch on the computer, you get something. Then the computer will tell you, okay, this is probably the best solution. If we would know that we will be looking at a bridge, then we would use different models, right? And we would use definitely the temperature in here, and we would be able to accommodate for this. What I also expect is that for other bridges, maybe like the one over here, you have not so many points, and this is probably because the deformation is so big over there that you miss the points. So actually there are measurements there, but just in this visualization and in this processing it didn't show up.
But actually for first one bridge it's also one probably confusing moment that in last couple of years it's partly renovated. So they remove asphalt part by part and then put it back, and if we measure these millimeters, it also can take an impact on that.
For this particular bridge, you mean? Yeah. Yeah, I don't know the bridge, but what I expect is that there is not only the asphalt, but there's also an iron construction or something else that is reflecting. Huh? So you have so many reflections over here that I think this is not just the asphalt, right? The asphalt would more have specular reflection. So there, you can have a look. Huh? So I don't know. We can go to Google Maps or simply have a look. But so the reflections here come from objects on the bridge.
If we had like 10 years or something, then would there be any points to still have this horizontal? Or there would be no choice, but you would have to go up.
What do you mean if you?
Had 10 more years at that time, if the trend line is there's some kind of angle, then
yes, so it could very well be. Yeah? So it's just an algorithm, right? It checks which is what fits best, and it depends on what you tell the algorithm to do, right? So if so this has a lower quality probably because the deviations with the linear model are quite high. So if I would change the quality, the points would simply drop out. I'm pretty sure if I would, for example, change it now here to the point quality to exclude the best ones here.
I'm just asking because I'm wondering if someone would want to use this data for, let's say, bridge health estimation or something, we could also say, oh, maybe just a wrong algorithm.
Yeah.
Let's ignore it.
Yeah. No, so the key message for me is that if you want to monitor the bridge, you should keep in mind what kind of data processing you do, right? So basically here I call this always a one-size-fits-all solution, right? So it's like the trousers or so. You are not gonna get a perfect solution. It's a one-size-fits-all. If you're interested in a particular thing, you would definitely tune it and get a better result. Did anybody see another interesting phenomenon in here? Anybody found something interesting?
So this picture is for both bridges.
The more bridges?
So this picture plus minuses for both bridges.
Sorry, it's a little bit far. I cannot hear you. The other bridges. So here, for example, this bridge, again. Oh. This one. Is this a question why there are no points over here?
Also a question. There's a big error.
So very strong signal, right? And I'm pretty sure indeed that if you would go further, that some of these points here would have too big residues, and therefore, because we set the threshold at 0.4, that's why they're kicked out over here. But if you look at the orientation, so the ascending image is looking, flying here, looking at this direction. So it would be perfect to get measurements from this. So that could be an explanation. It could also be that, like you were saying, that there is something done with the asphalt or something changed over here that's simply not coherent anymore. That, of course, could also be a possibility. I guess you've all looked at the red areas, right? So here maybe like a building which shows something peculiar. And what you can do here also is you can kind of select those points on the building. And if you are interested in analyzing this further, so I have now 161 points, so this is how this building moves. We have the histogram, we have the time series. Yes, there are definitely something changed also, right? So there are different segments of different behavior. But what you could do now is here simply download the CSV file. So if you want to check this with MATLAB or with Python or Excel or so, you can now click and open this file. And then for that subset, you could try to interpret this further, right? So here you have all these numbers, the latitude, the longitude, and then all the displacement numbers are here in the CSV file. Okay. Any other comments on this? Could have a look at the questions again. I think most of the things I just discussed now. We have the displacement rate, red and blue, direction of displacement, so towards the satellite, away from the satellite, changing the sensitivity of the color wheel, and that depends on what you want to see, obviously. Then there is the time slider below here. Right, so where we can select a certain limited time frame and see how things behaved over time. So we have, for example, this part, and then we can shift that for different sub-blocks. And like I said here, so here this is probably atmosphere that you're introducing at some point. All right. Okay. I think I covered most of the aspects here. The bridge, phase ambiguities we already discussed, the railway, the airport. Right, so the airport is very stable here. I think it's not the international airport, right, but a smaller airport somewhere close by. Something happening here at the edge, maybe. This may be something to look into. Yeah. Okay. So that was about the interaction with the portal. Let's see with the time that we still have, let's see if I addressed all the questions. I think I addressed a bit of the GPS thing, also the relation to the uplift, because with the IGRS you can do that with the GPS together and the gravity and the INSAR. I still have some of you who are interested in the PEAT story. I can give some feedback on that. Is there anything else that you want me to discuss? Yeah?
Expanding or collapsing of all orb, have you calculated?
Like averaging.
If you take data across the world, integrate them together, then can you say about this difference, what is happening reserved? So it's expanding a little bit collapsing a little bit.
I'm not sure what you exactly mean with collapsing and expanding. So.
So this node is getting radio is getting bigger or.
So indeed now we took Riga as an area.
About Earth, about all Earth.
All Earth, okay.
If you look to the big picture.
Yeah.
Is Earth shrinking?
Yeah. Okay. Got that.
This data.
Is Earth shrinking or that? Good question. Well, if you go to very big areas, you can look at this Copernicus map that I showed you in the beginning for the whole of Europe. Really the big signals, you really need to combine it with different techniques, and this is mostly because of the drifts that we can still have in the data. So if you have long time series of long areas or long spatial ranges, we have trends, for example, due to the troposphere or due to the ionosphere. We go to high latitude. We also have ionospheric effects, and that may introduce tilts in the whole data set. So usually what is done in that case is that also GPS stations are used to, for example, for the isostatic uplift in the Baltic, that is accommodated there. So I think at some point there is probably, you will introduce artifacts. But in principle, you could do it, right? So you could simply connect everything together. Yeah.
Because if you look to all these deltas across the wall, just zoom them.
Yeah.
And let's see.
Yeah. I think part of this has been done. So there have been papers where, let's say, all the delta areas of big rivers have been compared, because that is also where subsidence occurs. But yeah, you can do these exercises. Yeah. For example, what is interesting now, Google Earth Engine has a lot of these data in its repositories. The only thing for the SAR is that it only stores the amplitude data and not the complex data yet. So we cannot really run the Google Earth Engine on this. Otherwise, you could much easier still make a lot of interferograms. Yeah. Anything else? Shall I share something about the peat soils and that part?
Well,
yep.
Maybe question, how long it will be available, the exercise or demo that you provide?
Whether this is reliable?
No, available.
Available, okay. So what I asked here, so it says the trial data not Q8, so there is no quality assessment in it. So it's simply processed just to be able to show something here. So I think it is also temporary. I'm not sure how long it will be open. But I think that if it's going to be used, then it's good to do some quality assessment first, so that we, for example, we have scripts that kind of find these kind of unwrapping errors, and then
not used for decision.
Yeah.
It would be interesting discussions with colleagues and so on.
Yeah. Well, what I can definitely, so if you find it interesting to do something with it, I can make a special account, and then you can have a look at that. Okay. So now everything is under my account for the course, but I can make it available. Yeah, okay. Yeah, that's fine.
Can we say something? How is it different from this EGMS?
Yeah, the question is, how is this kind of product different from the European ground motion map or surface? Actually, I don't know exactly how this is computed. I think what you should see here is that there is probably the time difference. There's a time difference. I guess they go a bit further back in time.
Actually, it doesn't go that further in the future.
Oh, not so much. Okay.
2020.
Yeah. So there is, I think, also a decomposition in this east and up done here. I think you can select that. But like I said, I'm not so in favor of that because it is biased. But in principle, it uses the same data, and this, I think, more or less the same philosophy. And, yeah. Okay. Let me see. The gas fields also.
Do you know what is the time period over which the European land motion map has been completed?
I have to check. I don't know by heart. Yeah. Okay, so what is on the screen now is about this underground gas storage, where some of you were interested in. So this is an underground gas storage in the Netherlands. What you see here is the outline in blue of the location where the gas is injected and produced in the winter. And the little stars here, these are injection and production wells, so where the gas is produced. Now, if I click on this, you can see the time series. Let's look at it a couple of times. So you can see now how these the land is coming up and is going down. So now we're heading towards the winter. So we see now here winter comes, and here it's subsidence. Now we have subsidence, the gas is extracted. Now we're injecting gas again. Now it's extracted again. Now it's injected again. And now it is withdrawn again, produced again. So basically the idea here, so if you have this gas storages, you could now use this, for example, to, if you want to, if it is somewhere where you're interested in, you could try to compute it with the porosity and the permeability of the rock to see how much gas is there, what is the pressure of the gas inside. And what is very important here is that there is this fault, this black dashed dot line, that's a fault. And what you can very clearly see is that the subsidence and uplift rates here are very strongly delineated by the fault here. So there is nothing happening here on that side. So whereas here it goes over the reservoir area, here it's quite limited by this fault. So the fault is really like an impermeable fault, where the motion is not doesn't cross. So this is the up and down motion of the ground with gas injection. Okay, that was one thing to show you. Okay. Okay, so for those of you who are interested, here's another little story, and this is about the fly curtain. You know, if you have a caravan, you have these kind of strips that are hanging in front of to keep the flies out, right? And usually they have this very nice colored pattern. And so I call this the fly curtain because it's very useful in our analysis of data. Okay, let's try to this is quite a mathematical thing. So basically what we have, if we have a phase observation, is what we call a multi-modal probability density function. So that is what you see over here. So this is basically like if you have a Gaussian, you would have a single unimodal function. But because our phase has ambiguities, there is a higher likelihood for some phases and a lower likelihood for others, right? And this goes on until infinity. Now, if you have a probability density function like this and you simulate an observation, it will most likely be very close to the peak, right? So it will be less likely that it's at the edges. So what we can do now is we can. I need another dimension, so I'm going to introduce a color to see where we are on this multimodal PDF. So if we're at the top, 1, then I call it yellow. If we're at the bottom, I call it purple. That means that this particular picture, if I flip it here, this is the measurement, and here we see basically this hilly terrain for the PDF. I hope that you follow me over here. Okay, And here I just rotate it because for my fly curtain plot, I need to have it in this direction. So now the PDF is over here. These are the different ambiguities. So every cycle I have a new ambiguity. And this is just an arbitrary dimension. Okay, now I'm going to introduce more observations. And actually what I'm going to do is I'm going to use some real data. And this is peat soil. What you see here in the green line is not INSAR, it's what is called an Extensor Meter. So it's an instrument that is being put in the ground. Well, the only purpose is to measure is the deformation of the soil due to peat oxidation, raising groundwater tables, drying out of the soil. And actually it's extremely interesting because if you look at the vertical scale, so it goes up to maybe 17 millimeters up, and maybe also 70 millimeters down. So here we have, let's say, 3.5 centimeters of variation over the seasons. Here is days on the horizontal axis. So here we have a bit more than 2 years in terms of days. And basically what you see is that this is winter time. This peaks over here. Then the elevation of the soil is actually quite high. And in summertime, the ground dries out. So basically the big picture is a pattern which we call hysteresis. Hysteresis is a periodic pattern which is not symmetric, so to say. So basically the drying out of the soil goes very smoothly over here, but then in the fall when it gets wet, it goes up very, very quickly, right? And then it's winter time, and then summer comes again, it dries out, and it goes up relatively quickly. Okay, so first of all, the first message is, okay, so this is extremely dynamic motion, right? 3 centimeters up every time, every cycle. But actually it gets worse because if we look at the smaller scale, so the interseasonal variability, we see a jump, for example, from here to here, which is maybe about a centimeter. And this happens within maybe 2 weeks, right? So a centimeter of motion in 2 weeks can be very, very difficult to follow. And this is basically due to precipitation, rain. If there's a rain event, it will swell up, then it will dry out very quickly. Now the black dots are what I get if I have daily observations. So then I really, every day I can more or less sample the green signal. That's okay. But if I have satellite observations, and here I use TerraStar X, so that is every 11 days, so very similar to Sentinel, I would have only the red dots every 11 days. Now, if you look at only the red dots, you can see that it already becomes very difficult to follow all the peaks, right? So there are several peaks which I will not sample simply because it happens within the cycle of the satellite. So the variability of the signal, the peak going down and going up over here, I would completely miss that if I simply only have the TerraStar X data. So the first thing with peat is that it is extremely dynamic. So within a day or so, it can move quite considerably. Okay, so I use that as my ground truth. So here again, you see the truth. The green line is the truth. The red dots is the samples if I would have perfect observations, right? So there's no satellite data involved here. I just assumed TerraStar X every 11 days in a sample so that I have the red dots. So if I look at these dots over here and I plot them here, so they're over here, then I need to wrap them because I can only measure 360 degrees. So everything less than minus half a cycle and plus half a cycle, or minus 180 degrees plus 180 degrees, that gets wrapped back into this principal interval, right? Because I cannot measure more than one cycle. So that means that it will become very, very complex because I don't have the red ones. The red ones are actually mirrored over here. So I have this complex mess of points, and from this complex mess of points, I want to reconstruct the green line. It's very complicated. So that particular point, which is up there, should be here if I would be able to measure an absolute phase, but I'm not. I only can measure a wrapped phase, so this point is now ends up over here. And that happens for all these points which are outside the principal interval. Okay, so again, now I have this pattern, and now I'm going to use my fly curtain. So this is the fly curtain that I was talking about with the PDFs. So in this case, I know the truth. So I know where the center of each peak, where the yellow bar should be. Right? It should be right at the location of the red dot. And it is here, because I simulated it myself. The width of this pattern, how wide this is, sometimes it is wider, the other times it's narrower. For example, here the yellow part is quite wide, and maybe here the yellow part is very narrow. That is a quality of the phase quality, the coherence that I get. So basically, this is the truth, the positions where my observation should be. But the yellow part here are also the ambiguities. Now, if you already look at this from, for example, this location over here, and you would follow the yellow lines here, then you would never choose to go from here to this step, right? You would simply continue. This would go on, and then maybe here you would decide to go down, right? So this jump, I think that happened over here within 1, 2, 3, 4, 5, 6, 7, 8, maybe 9 days, more than a centimeter of uplift would be completely missed with this data, simply because the signal is so dynamic. And this is in the case that I have no noise. I have perfect data because the red dots are still in the center. So here you can see the magnitude of the problem. Okay. So now we can introduce noise. And so what we can do is, so if we know the truth here, that's what I just had. Now real data will be distributed somewhere around this PDF, right? So if you give me, if you tell me that you have a Gaussian PDF with the peak at 10 centimeters per year and a standard deviation of 1 centimeter per year, I can simulate 100 observations in that distribution, and most of them will be in the peak, but there will once in a while. If you have a Gaussian, 5% of your observations will be more than 2 sigma to the left or to the right. Now here I have 80 observations, so if I have 5% more to the left or to the right, there will be several which will be actually quite far off. For example, this one over here. Right? Most of them are very close to the yellow band, that is the peak of my PDF, but some of them are not. Some are in the edges, and this is what you would expect normally with data. Now this is now also wrapped because these values need to be inside the principal interval. So from here, we need to go here. Right? So all these values are now within this interval. So this is just to give you a feeling of the magnitude of the problem that we're facing mathematically, to try to reconstruct this signal that we were interested in from the red dots that we give over here. Because here we see the PDFs, but in reality, of course, we don't know the PDFs. So in reality, we have this. So this is this is the data, and this is data which really makes sense. It's truth extensor meter data plus realistic noise. Okay, so how can we solve that? So here, this is the combined image, right? So the true data are over here in green. The true rep data, so everything just in the principal interval is in blue, and the measured rep data are in red. So I need to reconstruct the green line from the red dots. That's the problem. Okay, so let me show you what we've been able to do here. Oh yeah, so this is also an important concept. So we call this loss of log. It's a new term, I guess, which is quite useful. Loss of log means that if there are connections between a time series and we sometimes lose the connection, then we basically get 2 time series. We cannot connect them together. So suppose that at this time, suppose that this would be an agricultural field, and the farmer would come here and plow the field, right? So then at this moment we get a loss of log, and the phase value that I get after that loss of log can be an arbitrarily different, right? So it can be shifted like this. So I do get a phase value between minus pi and plus pi, but it would be very complicated from the phase values itself. You would simply draw a line through that, and that would be it. But if we know that we have a loss of log, we cannot connect the time series. So the thing that I would like to show you now is what we did to tackle this problem, and that is, let me see. Maybe it's a little bit too technical story, but let's see if I can I hope that you find it interesting. So this is the displacement time series with this fly curtain, so we don't know exactly where we are. This is the truth that we got from the extensor meter. So basically, for example, at this location, we need to take the decision to go up instead of going down, right? If you would look at this time series, you would probably estimate, okay, this is an outlier and I need to move on over here. Now, so the question that we asked ourselves, so in every time step, is it now more likely that we need to go up or is it more likely that we need to go down? And actually, that is a question you can answer, because if in that time step it rained, then the likelihood that the point goes down is almost zero, right? If it rains, it is a volume expansion, so it basically has to go up. If it was dry and the temperature rose, then not completely clear, but it's more likely that it goes down. So we selected likelihoods for each step on whether we should go down or whether we should go up. And we used a recurrent neural network. Let's go over this here. And in that recurrent neural network, we use the day of year. So we know what time of the year, so we know the season. We have precipitation records, so we know whether it rained or not, and we have temperature records. Then we use this recurrent neural network, and the output of that, I will not discuss the inside of the black box, but there's a probability of the point going up, the probability of the point going down, and the probability that it stays the same. Now these probabilities we can estimate, and we can train that using the Extensor Meter data. Now, this here was the displacement, the truth. And this here, this is the solution that we get with standard phase unwrapping. So basically what we did is estimate for each epoch a random noise on top of these of the truth. And then we let the algorithm go over and over and over and try to find the root. Now, so most of the times it will follow this route. These are the thick red dots. But sometimes here it takes another route, goes up here, and sometimes it goes down here just because of the noise in the data, just a little bit noise that tickles the thing one side or the other, and you come up at these different locations. So sometimes you come up here, sometimes you come up here, sometimes here, and sometimes here. So there are 4 locations where you can end up. Now, if we use this recurrent neural network, then basically we're reducing this dramatically. So actually, there are still 3 options. So sometimes we are too high and sometimes we're too low. Remember, the green one is the truth, but the extreme red ones are out. And if we now look at where do we end and how often do we end there, that is indicated in this graph. So with the standard result, we would usually be off. 0 would be the truth. Oh, we would usually be off. And with our recurrent neural network using precipitation and temperature, so contextual data, most of our solutions are actually in the right direction. So the point that I'm trying to make here is that so this phase unwrapping, estimating the ambiguities, is something that is very complicated. There is no true solution. Sometimes if the signal is so dynamic, it's almost impossible. But the trick to try to improve is to use information from the outside, information from precipitation, rainfall, maybe a land use, that could help in finding a better solution. Okay, so this last part was basically into our research thing, just to tell you what we're working on at the moment. I think that's a good point to kind of wrap it up. So what I tried to do today was to give you an overview of INSAR, so how it worked. We start all the way in the beginning with this intuitive feel of the sensitivity to topography, on the interferograms, why it is that we can measure deformation 1,000 times better than topography or elevation. We also looked at the different processing steps, how to get there, and at the precision levels of the observations. We looked at what influences that precision, so not only the temporal variation of the area, but also atmosphere and the orbits, all these things we talked about. And in the end, then we really moved to the time series approach. And I hope that I have been able to convince you that if you use this as hundreds of images, or 133 in this case, this enables us to really dramatically beat down these error sources like the atmosphere. And we still get then a large many, about 2 million good measurements over one city, like Riga. And we have data that we can analyze. And I also hope that I've been able to show you that some of these analyses are practically meaningful, right? They can be used to monitor an asset, to plan ahead, to reduce risk. Yeah, I hope that that general overview gave you a bit of an idea of what INSAR is. If there are any further questions, I'm here, and otherwise I think it could be a good moment to wrap up here, right?
One
Question, yeah.
Variability has advantages in forestry application in comparison with optical, for instance, vegetation indexes or polarimetric radar. For instance, clear cutting, deforestation, detection, any advantages can be useful.
Yeah.
Yeah,
so I think so. The main difference between polarimetry using the amplitude data is that you're using it's geometry based, right? So we're measuring phase, which is related to a distance, and all these other applications of SAR are, I would say, more into classification or the physical interpretation of the signal and the amplitude. So in that sense, it's completely different what we do with interferometry. But different means also complementary, right? So that if we have data from the amplitude, for example, on the classes or the land use, then combining it with deformation could be a very strong and powerful source of information, right? So if we know what is causing, so for example, if the land goes down, therefore the groundwater goes up, and that changes land use, then you have a more complete story if you combine both. So you can search for those kind of complementarities, but I think in general it's also relatively different fields, right? The geodetic part is really like more geometry oriented, I would say. Yeah. Other questions? Yeah.
Are you waiting for any new satellites?
Whether there is a new satellite?
Are you waiting for any
if I'm waiting for a new satellite. Yes, definitely. So there are what is, for example, very exciting. Several exciting things, but one exciting thing is the L-band data. So we've been using, basically there is this geographic division where the US, the Americans have mostly been working on L-band in the past. The Chinese and the Russians have been mostly working in S-band. The Germans have been mostly working in X-band, and Europe has been mostly working in C-band. So there's kind of the frequencies seem to be geographically distributed. So now L-band hasn't been around for a long time. So we have Japanese satellites, but they were not so frequent, and it was difficult to get the data. So there is now SAOCOM, which is a mission from Argentina with 2 satellites. The data are not so available, but it's a bit of an issue. But they are in orbit. We have ROSE-L, which will be the next ESA mission, which will be L-band. And we have NISAR with the US and India together, which will be L-band and S-band together. So I think these different frequencies are going to be very exciting. There's Biomass, in another mission that is on the ESA table, which is P-band, that is even longer wavelength. So that is very exciting. What's also very exciting is that next Tuesday there will be the user consultation meeting at ESA for the next Earth Explorer. And there actually my colleague Paco Lopez-Decker from TU Delft, he came up with a proposal of having 2 satellites flying just before and after Sentinel, Sentinel-1, so that you have a mission concept with basically 3 satellites as a little train, where the middle satellite, Sentinel-1, would emit the signal that would reflect on the ground, and all 3 of them would pick it up. And that would give us more sensitivity, for example, for the north-south deformation. We can use it on the oceans, on ice. So there's a lot of very interesting stuff going on there. Let's see. So Sentinel-1 is planned now. So we have 1A and 1B. Sentinel-1C is ready. Basically, could be launched at some point, I think next year or so. Sentinel-1D will then be flying. So that means that we have a very long time series of Sentinel-1 observations, which is good for these kind of applications because we can really tie the same data together. And then we will probably go to the high-resolution wide swath data with Sentinel, so the follow-up, the next generation of Sentinel-1. So and probably I forgot a couple of things. The Japanese are moving further. There are all these commercial companies from Silicon Valley and ICEYE, I think, so from Finland, who are now currently having X-band satellites, and the data are becoming more available. So yeah, basically, if you want to engage in radar and SAR, this is the golden age, as we call it, right? So it's really exploding. So.
Maybe I can add something.
Huh? Yeah.
So, concerning SAOCOM, it's true that they were not so easy to get, but we just signed last week the agreement between ESA and CONAE to distribute to European users the SAOCOM data outside Europe.
Okay.
Because SAOCOM in Europe are distributed by ASI,
Yeah.
but the SAOCOM data outside Europe will be distributed by ESA.
Okay.
So it will not be routine distribution, so you cannot apply on a continuous basis to get this data all the time, like for Sentinel. You can apply for a quota, so quota could be maybe 20, 50, 100 data, but it's still good, because if you want, imagine that there are archive acquisition covering, don't know, 2 years of Latvia, well, Latvia is in Europe, sorry, but another region, then you can apply for a long number of acquisitions and then still perform monitoring over a few years over an area. And then hopefully in the later on it will become a real third-party mission, and then we can get a longer time series.
Yeah.
For the P-band, biomass will be launched theoretically in 1 year from now. So hopefully next summer we can have access, well, okay, will be during the Cal-Val phase, but afterwards you will get the P-band data. Of course, they will be with a very much coarser space resolution, so you cannot measure this type of accurate in space maps like the one that you can do with Sentinel-1.
Yeah.
And then what else? Yeah, Roselle, you mentioned it. Okay, but soon you might be able to make similar processing like the one that Ramon showed, also with the L-band, P-band, C-band, and then compare. Of course, you will not find exactly the same points, because maybe due to the different band or the different incidents, the persistent point will be different, but still you can compare the maps and combine the results somehow.
Yeah, definitely. Yeah, good question. So the other thing I would like to mention, it's not only the satellites that are there, but it's also, I think what you see now is that there is this tremendous increase in processing capabilities, understanding of the problem. So some of these things become more like a commodity, like this ground motion surface is just there, right? So the thing that I always would like to stress to people like this, although you are from very different backgrounds, but is that we should not basically see this as a product that is just simply there and it's done, it's on the internet. But like I showed you, there are for every application you need a different approach, right? And this is why we need people. We not only need software and tools, we need people who understand what they're doing. And I think that is very, very important. And I want to stress that because we're basically creating the impression by making these maps also freely available that it is already done, right? That there is no development necessary anymore. And so I'm from TU Delft, and for example, we saw that at telecommunications engineering, once the cell phones were there, and it seems to be the end of the development, and so no students wanted to study electrical engineering or telecommunication anymore because everything was already there, right? It really dropped. And I'm very anxious that the same thing would happen in our field of geodesy and geomatics, understanding satellite data. So it is not so that because the data are online that it is done. We still need people who are understanding how it should be interpreted and to tune the data for a particular application. And I think there are also, for those of you who are still students and developing, I think so the company that we selected here with SkyGeo, I think there is much more opportunity for companies like this, right? So we need to approach users and convince users. So the most part of my career I've been talking to people and trying to convince them that this data is useful. And you see that it takes a while before this is picked up, but now you see that it is really taking off tremendously. You have civil engineers, railway engineers, structural engineers, all these people, city planners. They are using this data and they want it, right? So it means that there is a good development curve. Other questions? If not, I would like to thank you very much for your attention, and yeah, good luck. If you want to drop me an email or so, or have other questions, then I guess you know how to find me. Yeah, thank you. Yeah.